This is the final presentation, analysis, and redesign of a mechanical juicer of Team 4 that is made up of Alberto, Álvaro, Luis, Leonardo, Zachary, and Robert. About the part. A mechanical juicer is a device designed to extract juice from fruits using only manual force, efficiently separating the juice from the pulp and seeds. The primary customers are mainly homeowners, and the secondary customers are restaurants and cafes. Annual estimated demand is of 2 million units, and the estimated production volume is of 200,000 units. Here is the CAD model that represents the collapsed and exploded views of the mechanical juicer. And here we can see a video of how the assembly for the mechanical juicer originally works. Functional analysis. The fast breakdown shows how the core function of the mechanical juicer is to extract juice, while subfunctions include pressing the fruit, filtering the juice, or assuring dependability and convenience.
Here we have the function component mapping matrix. We can see that apply force and ensure stability are the functions that are most repeated through all the components. This makes sense as apply force is the main feature that this juicer does, and ensure stability is a feature that's really needed because of the mechanical complexity of the machine.
This is our quad chart, which compares functional importance and manufacturing cost, where high manufacturing cost is to be above $4 per part. Based on analysis, it would be ideal to eliminate the bar and interesting to redesign the strainer, reciprocating link, anchor, and base, while most likely keeping the other parts unchanged. Next, we will discuss the product family design. After reviewing the functions in the fast diagram and considering both our primary and secondary customer groups, we determined that only one function needs to differ, hold fruit. This is because our secondary customer group requires different holders for different fruits, so that variation in function is necessary. The unique modules associated with this function are the holder, the strainer, the movable jaw, and the funnel. The base will also vary between customer groups to adapt the mechanical juicer to their specific needs.
Design for manual assembly, we focused on three parts that were high manufacturing costs, those being the bar, the anchor, the base. The bar and anchor are part of our platform, while the base is modular. The first things we'll do is reduce the bar count and reduce the fasteners, and then we'll prefer a snap fit for the anchor and base. Looking at the modifications made on the last slide, we can see that the design for manual assembly, the post-DFA time gets more efficient by nearly 6%.
Here we have the design for automated assembly. We decided to analyze the subassembly of the base, anchor, and the bar because the bar has a high manufacturing cost and low functional importance, so we should redesign that. Before the DFA, the cost of the assembly would be $69.2, and after DFA, it reduces to $11.12. Here we have the CAD for design for automated assembly. We can see that now the bar and the anchor are the same piece, so we reduce bar counts. Also by doing that, we reduce fasteners, and by doing that, again, we reduce bar variety as those fasteners were not the same as other fasteners used in the juicer. Also, we decided to connect the anchor with the base with a snap fit.
For the metal part, the strainer was selected as the component to be redesigned. It is an aluminum piece where the fruit is squeezed. Taking into account the material, the shape, the mass, and other specifications, the selected manufacturing process was sheet metalworking.
When looking at design for manufacturing, the first part we'll look at is the strainer. This is a metal part that was used to strain the juice from pulp and seeds. Some of the major changes that we'll focus on are avoiding the narrow features, such as the holes that are very closely together and can lead to deformation in the bending process. Next, we'll focus on the small holes, which are generally described as being smaller than the thickness of the material. Lastly, we'll focus on the sharp bends. The bends, as seen in the original design, are almost 90 degrees, making it hard to remove from the mold. The new design uses a more dome-like structure with more spread out holes, allowing for a easier forming die. Overall, reduces the cost of the die and reduces the material cost since there's less material being formed.
For the plastic component, the decision was made to redesign the funnel. Since it is made of polypropylene, 7 different processes were possible, but its cylindrical shape narrowed the options down to 3. In the end, the only process capable of meeting all the specifications was injection molding.
On this slide, we have the original funnel design before any DfM improvements. This version was modeled using a revolved aluminum geometry, and as you can see, it had several manufacturability issues for injection molding. From the mass properties report, the material was 6061 aluminum with a mass of about 150 grams and a volume of 55,550 cubic millimeters. The wall thickness averaged around 1.3 millimeters, which is below recommended injection molding guidelines. The tolerance was set to plus or minus 0.35 millimeters, and the surface finish wasn't critical at this stage. When I ran DfM Pro, it identified 3 main problems. The draft angles were too small, the wall thickness was non-uniform and generally too thin, and several sharp corners needed to be rounded. These issues would create challenges of mold release, flow consistency, and tooling durability. This analysis guided the redesign shown in the next slide. After applying the DfM recommendations, I redesigned the funnel specifically for plastic injection molding using a polypropylene copolymer. The new mass reduced significantly to around 70 grams, and the volume increased slightly due to more uniform geometry. Most importantly, the wall thickness was increased to a consistent 2 millimeters, which improves part strength and reduces cooling time variation. I added a minimum 5-degree draft angle throughout the part to improve mold injection, and I applied 2 millimeter fillets to eliminate sharp corners and help plastic flow more smoothly. These changes improve manufacturability without affecting the funnel's functionality. Overall, the redesign reduces material cost, lowers mold complexity, and provides better performance as a food-safe injection molded component.
Product service system enhancement with software services would incorporate the user to support the owner of the item through an online magazine. Juices and drinks, G&D, magazine would contain a number of different drinks, recipes, and other food-related items that users could take inspiration from. The magazine would be available online on our website for any users logging. It would additionally be available for download to subscription members for personal printing. Additionally, suggestions would be taken and competitions held for additional items to be placed into the magazine. Users would contribute any potential ideas or any other uses for the product. The magazine would benefit the consumer financially by not having to buy pre-made drinks and have everything needed to make whatever they want at home. Consumers may also additionally not purchase any other cookbooks related to the topic, saving them more money. Environmentally, the magazine can provide exact information on how much of the ingredients to use, reducing overbuying and a potential waste of food. Potential future revenue could include advertising in the magazine and a premium subscription to receive a shipped magazine to your house, along with a different exclusive strainer. The DfA improvements made that the assembly time loss is 32 seconds. We gain a 6.3% efficiency. Also, the automated assembly reduced the cost by $58.08. The DfM improvements reduced the strainer foaming die cost to $12, and also the final die cost. Critique: we should improve viability potential really in this model. The CAD dimensions are smaller than the real-world estimates, and we should analyze further material optimization for reduced prices. Also, new approach for the future is to look into a change design to reduce overall material.